Welcome to the course Excelling with Mathematical Modeling. In this particular session, we will be solving some typical problems on stability analysis, namely using this Lyapunov function. So, to start with, let us consider the dynamical system dx dt equal to y and dy dt is equal to minus a sin x minus by, where a, b are constants greater than 0. So, if you recall the Liapunov function, which we have taken to be vxy. So, if you can find a Liapunov function vxy such that this is positive definite, v00 has to be 0, assuming 00 to be the equilibrium point or critical point or fixed point. If you assume that to be x star y star, generalize it, so you can put them as x star y star, and v dot, this has to be negative semi-definite. So, by this I mean this has to be greater than 0 for all x y not equal to 0 0. This has to be less or equal to 0 for all x y not equal to 0 0. And if it is just negative definite, for this it is Lyapunov stable, and for this it is asymptotically stable. Now, in this particular problem, you have to choose, and again I say that there is no hard and fast rule, you have to figure out by yourself and it will come with practice. So, in this particular case, it cannot be x square plus y square because we have some sin x here. So, you have to choose it in such a clever way, 1 minus cos x plus some half y square. You will understand why this half has come. If you do not take a half here, you will face some problem and ultimately you will bring that value to half, so which you will realize soon. So, this is greater than 0 for all x y not equal to 0 0. This is obviously true because it contains a square, and we know that the value of cosine lies between minus 1 to plus 1. So, this value is positive also for x and y not equal to 0 0. A and b's are positive constants, and hence this is greater than 0. Now, if I put x equal to 0 and y equal to 0, I see that the right hand side has been satisfied. So, 0 0 is my equilibrium point. So, I find v00, which is equal to a 1 minus cos 0 plus half 0 square, and the answer is 0 because cos 0 is 1 and this gives you 0. Now, let us calculate v dot. So, v dot is del v del x into x dot plus del v del y into y dot. This is equal to del v del x. So, a sin x into x dot, which is y. From here, del v del y, it is half into 2y into y dot, which is minus a sin x minus by. So, it is a y sin x, this and this cancels, minus a y sin x minus by square. So, the coefficient of this particular term becomes minus 1 only if you choose this value to be half. So, if you choose it something else, suppose I keep it only y square, this becomes only 2y. So, minus 2ayx, then I will not be able to prove that this is negative definite. So, to make this one and this one cancel, this particular constant has been chosen. So, as I have told you that there is no hard and fast rule, it will come with practice, and at the same time this Lyapunov function is not unique, it can take any form. For one form you may get the conditions to be satisfied, from other forms you may not. So, you have to keep on playing with it. So, this you get minus by square, and this is less than 0 for all x y not equal to 0. So, this satisfies negative definite, and you can say that the origin is asymptotically stable. So, this is one particular example where we have a non-algebraic term, mainly the trigonometric term as sin x. Let us move to the next example. So, dx dt equal to y and dy dt equal to minus x minus y. So, let us choose Vxy equal to 2x square plus y square. So, as you can see, this is always greater than 0 for all xy not equal to 0 0. V 0 0 again is equal to 0. So, from here I can see that if I put this equal to 0 and this equal to 0, I will get 0 0 as my equilibrium point. And now comes V dot. What is dv dt? This is del v del x into x dot plus del v del y into y dot. This is equal to, so 4x into y minus del v del y is minus 1 into y dot minus x minus y. Sorry, this is 2y del v del y from here. And if I simplify this, I get 4xy minus 2xy minus 2y square. So, here I get 2xy minus 2y square. So, the conclusion is, with this form of Lyapunov function, your definiteness cannot be determined, hence I cannot conclude about stability with this form of Lyapunov function. Now, to make these two terms to cancel each other, so if I just take this to be Vxy equal to x square plus y square, then you see that here your V dot will be 2x into x dot plus 2y into minus x minus y, and this cancels and this becomes less than 0. So, this is exactly what I was telling, that with one form of Lyapunov function you may get to prove the stability of the system, and with another form you may not. So, you have to choose your Lyapunov function cleverly, such that everything, all the conditions are satisfied. Now, let us take an example where if it is an algebraic terms on the right hand side, like minus 3x cube minus y and dy dt equal to x to the power 5 minus 2y cube. Now, this right hand side, as you can see, there are higher degrees of polynomials. In that particular case, an attempt can be made like this, that you choose your Lyapunov function in this form, where your a, b's are positive constants, and from here you can see that 0, 0 is your equilibrium point. Now, you have to find a suitable m and n here. So, what you have to do is, so the first two properties are satisfied, that this will always be positive for non-zero x and y, and at the point 0, 0 they become 0. So, you start with v dot, which is del v del x into x dot plus del v del y into y dot. So, del v del x 2am x to the power 2m minus 1, and x dot is minus 3x cube minus y, plus 2bn y to the power 2n minus 1 and x to the power 5 minus 2y cube. So, instead of guessing the values of m and n, this is a systematic manner by which you can find the value of m and n. So, 2am x to the power 2m plus 2 with a negative sign. So, I am just multiplying, minus 2am x to the power 2m minus 1 into y, plus 2bn x to the power 5 y to the power 2n minus 1 minus 4bn y to the power 2n plus 2. So, this term is fine, this term is fine. The problem is with these terms, which are called indefinite terms. So, you have to choose in the values of m and n in such a manner that these two term cancels out. And for that, what you have to do, the power of x's and the power of y's has to be same. So, here it is x to the power 5. So, you choose 2m minus 1, or you can write x to the power 2m minus 1 must be equal to x to the power 5, which implies 2m minus 1 is 5 and m is equal to 3. Similarly, you can choose y to the power 2n minus 1 is y. So, y to the power 2n minus 1 will be equal to y to the power 1, which implies 2n minus 1 is 1 and n is equal to 1. So, m equal to 3 and n equal to 1 gives you the Lyapunov function v dot equal to minus 2a. So, m is 3, sorry, here it will be 6 actually, 3 into 2. So, minus 18 a x to the power 8 minus 6a x to the power 5 y plus 2b x to the power 5 y and minus 4b y to the power 2n, so 4. So, you have got the powers of x and y is same, but now you have to choose your values of a and b in such a manner that these two cancels out. So, if you choose a equal to 1, this is 6, and b equal to 3, this is again 6, I will get v dot equal to minus 18 x to the power 8, this is minus 6 x to the power 5 y plus 6 x to the power 5 y and minus 312 y to the power 4. So, this 2 cancels and this is always less than 0 for all x y not equal to 0, 0, and hence the system is asymptotically stable. If you want to check the global stability, so you have to show that the system is radially unbounded. So, what does that mean? It says that your Vxy must tend to infinity as the norm of xy tends to infinity, norm. So, by norm you mean the distance, and here it is the distance of x y from the origin, from the equilibrium point. So, if you use the distance formula, it is x minus 0 square plus y minus 0 square by root. So, this is your x square plus y square. This is the norm of x y. So, your v is of the form, now you know what is your a and what is your b. So, it is x to the power 6 plus 3y square. So, as your x tends to infinity, your y also tends to infinity, your norm means this one, this also tends to infinite, and your v also tends to infinity. So, you show that the system is radially unbounded and hence it is also globally asymptotically stable. So, this is another technique of finding this expression for Lyapunov function, but it works on only in certain sets of problem where the right hand side are higher powers of polynomial. In our next example, we take an equation and prove where you have an equilibrium point x star y star which is other than 0 0. So, dx dt equal to x minus xy and dy dt equal to minus gamma y plus xy. So, let us take this particular example. So, if I say x minus xy equal to 0, x I take common, 1 minus y equal to 0, which gives x equal to 0 and y equal to 1. My second equation is minus gamma y plus xy equal to 0, I take y common, minus gamma plus x. So, if I put x equal to 0 here, I will be left, left with the term minus gamma y equal to 0, and this is not equal to 0 implies y equal to 0. So, one of the equilibrium point is 0 0. If I put y equal to 1 here, then I get x equal to gamma. So, gamma 1 is another equilibrium point. This time we will be checking the stability at the point gamma 1 where gamma is a positive number. So, if I use Lyapunov's indirect method, then I have to write the matrix fx, fy, gx, gy, where this is equal to some fxy and this is equal to some gxy. So, if I calculate this, fx is 1 minus y, fy is minus x, gx is y and gy is minus gamma plus x at the point x star y star, and in this case that is gamma 1. So, if I substitute this, this is 0, this is minus gamma, this is 1 and this becomes 0. So, the eigenvalues can be calculated from this characteristic equation, which is minus lambda minus gamma 1 minus lambda equal to 0. So, this implies lambda square plus gamma equal to 0 and lambda equal to plus minus I root gamma. So, this gives a center because it has only imaginary roots, which is stable but not asymptotically. Now, this is Lyapunov indirect method. Let us now use the Lyapunov's direct method, where we use the function vxy and instead of taking 0 0, we take gamma 1 to be our equilibrium point. As I told you, the Lyapunov function, they becomes typical for a particular problem. Like in this problem, let us define a function hxy, which is say x star log x minus x plus y star log y minus y. Now, obviously, you will be wondering that how suddenly this function has come. As I told you, it will come with practice and with various examples, where you will see many forms of this Lyapunov function, and when you take an unknown problem, you will be able to figure out. So, here your x star and y star is equal to gamma 1. So, if I put it here, that is gamma log x minus x plus this is 1 log y minus y. Now, I define, so this is not my Lyapunov function, the notation remains the same, it is Vxy, this is equal to x star y star minus hxy. Now, why this has been done? Because otherwise, if you substitute the value gamma 1 here, this will not be equal to 0, and that is one of the condition. So, this will be gamma log x star minus x star plus log y star minus y star minus gamma log x minus x plus log y minus y. So, this is equal to gamma log gamma minus gamma plus log 1, which is 0 minus 1 minus gamma log x minus x plus log y minus y. So, I have gamma log gamma minus log x minus log y plus x minus gamma plus y minus 1. So, this is your Lyapunov function. Now, if you put gamma 1 here, so you are going to get gamma log gamma minus log gamma minus log 1 plus gamma minus gamma plus 1 minus 1, and this gives you 0. So, at the equilibrium point, the function vanishes. Now, let us calculate V dot. Before that, let me quickly, I think we do it here itself. Okay. So, if you want to calculate this V dot, the formula is del V del x into x dot plus del V del y into y dot. So, if I substitute it, I will get gamma by x minus 1 into x minus xy plus 1 by y minus 1 minus gamma y plus xy. So, it will be easy to calculate the the del v del x and del v del y from here, and you just substitute it here, and your x dot and y dot you get from the given differential equations. So, if you simplify this, you will get this is gamma minus gamma y minus x plus xy, and this is again minus gamma plus x plus gamma y minus xy. So, if you see that this and this cancels, this cancels, this cancels this, and you get this is equal to 0. So, which means that your gamma 1 is Lyapunov stable or stable, which coincides with the Lyapunov's indirect method. So, whether you use the indirect method or whether you use the direct method, in both the cases you get the same answer. The important question here is that you have a system which is nonlinear. However, you are linearizing the system, you are doing some analysis, and you are concluding on the linearized system. You say this linear system is a node or this linear system is a stable spiral, and then you conclude that on the nonlinear system. So, the question is that how sure you are that that is going to work, because all your analysis on the linear system, we say it is a linear stability analysis, whereas our equation may be linear, may be nonlinear, but we keep the result as the same. If it is linear, no problem, but if it is nonlinear, we linearize it first, then do our analysis and then conclude on the linear system, and then we say that our nonlinear system also follows the same kind of dynamics. Now, the question is why that happens. So, here what you see that I have written the differential equation of the form that say this is the linear part and this is the nonlinear part. Now, the hypothesis is that this determinant A, B, C, D is not equal to 0. Number 2, this P1 and Q1, they have continuous first partial derivatives for all x such that limit x y tends to 0 0 p1 x y divided by root of x square plus y square, this is 0, and limit x y tends to 0 0 q1 x y divided by root of x square plus y square equal to 0. So, if this condition is satisfied, then we have the following conclusions. So, here I write the linear system and here is the nonlinear system. So, this is your 1 and this is your 2, and we assume say these two properties has been satisfied. So, then the conclusion is number 1, yeah, of course, you will calculate the eigenvalues lambda 1 and lambda 2. So, it says that if lambda 1 and lambda 2, they are real, unequal and of same sign. If such thing happens, then 0 0 is a node for 2 and also 1. So, it is if 0 0 is a node for 2, then it will also be a node for 1. So, that is why it happens that you have linearized it, but you did not check this property which is automatically fulfilled, and then you conclude that 0 0 is a node for my linear system and therefore, it is also a node for my nonlinear system. The same thing is true if they are real, unequal and opposite signs. So, in that case you get a saddle. So, if your 2 shows that it is a saddle, it is also a saddle for your system 1. Similarly, the third one, if it is complex conjugate with non-zero real part, so complex conjugate real part not equal to 0, so then you get spiral or focus. So, if the system 2 shows that it is a spiral or a focus, then system 1 will also will have a spiral or a focus, means at the equilibrium point 0, 0. If they are real and equal with a comma d not equal to 0 and b equal to c equal to 0. So, if this happens, this one is a bit conditional, that you have to remember this, then your system 2, if your system 2 is a node, your system 1 will also be a node. And if it is purely imaginary, which is number 5, then here is a deviation, that if your 0, 0 is a center for 2, then for 1 it can be a center or spiral. So, this is one deviation that you get, that if it is purely imaginary root, we know that this is a center, but for 1 it can be a center or it can be a spiral. And similarly, if your roots are real and equal with the condition a equal to d equal to not equal to 0. Like here a and d not equal to 0, but they can be different values. But here if it is a is equal to d and non-zero and b is equal to c equal to 0, in that particular case 0, 0 is a node for 2, but for 1 it can be a node or spiral. So, basically I need you to remember this theorem, that yes, we have a theorem which tells you that though we are doing our stability analysis on the linear system, but the result is also true for the nonlinear system because of this following properties, and hence what we can say on the linear system is also holds true for the nonlinear system. Quickly we just take an example such that it is clear. So, you have this dx dt equal to x plus 2y plus x square. So, this is your nonlinear part. dy dt equal to minus 3x minus 4y plus 2y square. Again, this is your nonlinear part. So, the first property is a, b, c, d. So, a, b, which is 1, 2, c, d, which is minus 3 minus 4, and this is minus 4 plus 6, it is 2. So, it is not equal to 0. So, the first property is satisfied. And for the second one, I have to show p1 xy divided by root of x square plus y square, and this will be equal to 0. So, this is my p1, which is x square by root of x square plus y square. So, generally we solve this double limit by taking x equal to r cos theta, because it is in the form x square plus y square, and y equal to r sin theta, such that your x square plus y square is equal to r square, and as your x tends to 0, y tends to 0 simultaneously, your r will also tend to 0. So, if I now replace this by r tends to 0, so I have x square as r square cos square theta, and this is r square cos square theta plus r square sin square theta. If you take an r square common, then it becomes only r. So, r square cos square theta by r, this and this cancels, and you are left with limit r tends to 0 r cos square theta. Now, as we know, this cos theta is bounded. So, this is less or equal to limit r tends to 0 into r, and it is 0. So, the limiting value of this is 0. In the similar manner, you can prove that limit x y tends to 0 0 q1 x by root of x square plus y square is also 0. So, our whole property has been satisfied, and if you take the linearized system, that is x plus 2y and dy dt equal to minus 3x minus 4y, I find the eigenvalue at the point 0 0. So, 1, 2, minus 3, minus 4, minus lambda, and you can show that this lambda value is 5 plus minus I root 15 by 2. So, this is imaginary values with positive real part, and hence it is a spiral and an unstable one because this real value is positive. So, this linear system gives you an unstable spiral, and we conclude that the non-linear system will also give you an unstable spiral. So, that is how your theorem has been explained with the help of an example. So, in my next lecture, we will be talking about some growth models. Till then, bye bye.